Hello? Okay, good. Yeah, so it's my great pleasure to welcome today's ITC Colloquium speaker, Professor Glenn Starkman from Case Western University. Professor Starkman is a distinguished university professor at Case Western Reserve University and the vice chair of the physics department. Glenn has made significant and creative contributions to an incredibly wide range of subjects in theoretical physics. It's impossible to enumerate all of them. Just to give you some examples, for example, in the field of particle physics, he contributed to fine-tuning or non-fine-tuning problems of the standard model and the physics beyond the standard model. In the field of cosmology and astrophysics, Glenn proposed new forms of dark matter. He studied the properties of dark energy. He explored the possibility of novel topology of the universe, and he discovered some peculiar features of CMB that we observe. And also in the field of modified gravity, Glenn and his collaborators has derived the consequences of modified gravity on the motions of planets and moons, also known as the Lu-Starkman precession, and also the effects on the growth function of on the growth of large-scale structures. Besides these research works, Glenn also has made significant contributions to science communication and education. Glenn is the director of the Center for Education and the Research in Cosmology and Astrophysics, and he is the founding director of the Institute for the Science of Origins. So under Glenn's directorship, those institutes has fostered collaborations among researchers from a wide range of discipline, and also connects the universities, museums, and news media to engage both scientists and the public. So, so let's welcome Professor Glenn Starkman.
Thank you very much. It's great to be back here, and thank you for the lovely introduction. I wish it was really as good as that, but so I want to tell you something that I want to try to overthrow something that we've believed for a very long time. One of those fundamental principles of cosmology that we have grown up with. And so to do that, of course, I need to present extraordinary claims. I need to present some extraordinary evidence. So I want to try to do that. I want to try to convince you that the universe is not actually statistically isotropic. And this is work that I've been doing with a whole bunch of people, most recently with this collaboration that we put together of people all over the world called Compact. More about that really during the lunchtime talk. It includes students on the top row and a whole suite of postdocs on the second row. And of course, the people who mostly don't do any work, except for Craig, on the last row. Well, Tiago does a lot of work. The rest of us kind of sit in on telecons and discuss all the work that everyone else did. Okay. The specific project actually is something that Yashar Akrami and Craig Copey and I did last year and the year before with Joanne Jones, who's now a PhD student in astronomy at Chicago. Okay. So, you know, when we go out and measure the fluctuations in the cosmic microwave background, starting with COBE, you know, and then with WMAP, and getting better and better maps of the universe, the thing that we're always told to do is that we should take those maps and expand them in a spherical harmonic expansion. Why? Well, it's because our theory, our standard model for those fluctuations, tells us that the sky is statistically isotropic. And so those ALMs, those coefficients of the spherical harmonics, are independent Gaussian random variables, which means that the expectation of any pair of them is 0 unless it's the same one. Okay? And then it only depends on the L index and not the M index. So all of the interesting information, well, maybe not quite all if you're interested in non-Gaussianity, but nearly all the interesting information is contained in these C sub L's, and if we could just learn what these are, we would know pretty much all there is to know about early universe, large, cosmology. Okay. So we go out and we try to measure those C sub L's. We try to estimate them from the sky. And we do this absolutely amazing job. This is already a few years old, this particular one. I just happen to like the combination. But you see that we have a 6, or really should be 7 if you include curvature, parameter fit, to a lot more than 7 points. A lot more than 7 independent data points. C sub L's of temperature and of E-mode polarization and the cross correlation between them. Hundreds of different points on L's ranging from 2 to many thousands. So this is really completely astonishing as an experimental accomplishment and in terms of its agreement with theory. But the question is, so what that analysis, what those graphs showed you, is if you look at the C sub L's, do they agree with the theoretical prediction? But nowhere in there did we check to see whether it's really true that the ALMs are independent of one another, that one can really make this incredible reduction in the correlation matrix, that there are no correlations between ALMs. So shouldn't we check? And this talk will be about what happens when you check. And so it's about troubles in this isotropical paradise, whether you talk about the large angle problem or low L alignments or a silent hemisphere or parity. And as I said, the bottom line will be that the universe is not statistically isotropic. So let's go back to this, to COBE, to the Cosmic Background Explorer back in the 1990s. And the first hint that there was something wrong. This is not a COBE graph, but in the first WMAP graph, you look here at this is the C sub L's of the cosmic microwave background, and you see that the quadrupole is low. Okay? So on this graph, the solid line is the expected theory value. The gray band is the cosmic variance. The error bar due just to the fact that, for example, at L equals 2, there are only 5 different ALMs. And so the error in your prediction is quite big. And you have one data point, which is very well measured, but the error bar is very large. And you say, this is really strange. Okay, it's true that it's strange, but it's not that strange. Right? After all, in terms of cosmic variance error, this is kind of similarly anomalous, this dip at L of 20 and this bump at L of 40 and this dip at L of around 200. So why should we focus on this, on this low L anomaly? And the answer really is that you're looking at this graph in the completely wrong way. You should look at not the multiple moments of the graph, but the angles that it subtends. And so what really we should be talking about is not the C sub L's, the angular power spectrum, but the angular correlation function, which says take any pairs of points separated by some angle theta, multiply their temperatures, and average over all such pairs of points separated by that fixed angle. That's the angular correlation function, C of theta. Now, back when COBE was designed, this is what people would have wanted to measure because this is the type of thing that astronomers would have been interested in, not the angular power spectrum. But in the meantime, we developed a theory, and the theory told us to instead measure the angular power spectrum, which contains the same information as the angular correlation function, just differently organized. And so no one talked for a while about what the angular correlation function is, even though we know that often it's good to make transforms of your data because you learn new things. That's why we teach people things like Fourier transforms and Legendre transforms and all the other transforms that we do to data is because sometimes effects are pulled out much better in a transform. And so here is a paper that the COBE team published only in the 4th year of their analysis, or after the 4th year of analysis, in which they plotted the angular correlation function. And they didn't show you what's strange about this. Okay? People talked about it, and so I'll tell you what's strange about this in a moment when we look at what WMAP did. Because WMAP not only noticed what was strange about these graphs, but also put a number on it to tell us how strange. Okay. So, another decade goes by after COBE, and the WMAP satellite makes measurements of the same sky at higher angular resolution and higher signal to noise. And here actually is their third-year plot of the angular correlation function. The dashed line is the expected theoretical value. In other words, if you put in the expected C sub L's and write down that Legendre series, this is the curve that you'll get. And then if you make realizations and ask what's the 1 sigma band within which actual realizations lie, it's this blue band, and you should be very careful about doing something like chi by I with this because the errors are highly correlated across different thetas. But here is the data in the Q, V, and W band. Instead of doing this, going down to a big anti-correlation and then a bigger correlation, it does this. It goes down to a smaller anti-correlation, and then it just kind of sits there with 0 or nearly 0 correlation. And it does that in the Q band, the V band, the W band. It does that in this independent linear combinations map that was made, but only if you exclude the galactic plane. If you look at the full sky, it doesn't quite hug 0 in quite the same way, and you get this bigger anti-correlation up here. So if you take the part of the sky that you actually trust, namely the part outside the galaxy, and measure the angular correlation function, and if you take the bands that you measure, you'll see that you really get very little angular correlation above 60 degrees. And that's what we saw here in COBE. Okay, so WMAP put a measure on this. They said, let's integrate the correlation function squared to see how much it deviates from 0 from 60 degrees to 180 degrees, and they wrote down this statistic, the S1/2 statistic. Okay. So how unusual is this S1/2 statistic? Oops. Okay. There we go. Well, the expected value of this S1/2 is about 50,000 micro K to the 4th, and the value you get on typical maps, if they're on the full sky, is about 8,500, 8,600, somewhere in there. But if you take it on the part of the sky outside the galaxy, it's about 1,100 or 1,200. And that happens about 0.025% of the time. So a few times out of every 10,000, if you make realizations of the theory, which expects 50,000, you'll get a S1/2 as low as 11 or 1,200. So that is much more unlikely than the fact that the quadrupole was low. The quadrupole lowness has a p-value of about 10%. Okay. So this isn't a problem with the quadrupole. It's a problem with the angular correlation function at large angles. Okay. And it's interesting, if you look, what you'll find is that if you look at pairs of points outside the galaxy, you get this low correlation function. But if you include points inside the galaxy, you get something completely different. Okay. So perhaps those aren't the best measure of what's going on the sky. Okay. So I think what a lot of people expected, I'm not sure why, since COBE had seen the same thing as WMAP, is that when one went and did this again with new scan strategies and more sensitive detectors, that one would get something completely different. Okay? So people expected this to change in Planck, but it didn't. Okay? So exactly the same thing. You see exactly the same thing, and it doesn't matter which of the methods you use to remove foregrounds on the sky. You find the same thing, that none of the realizations they made had as low an S1/2 as one saw. Yes?
If you split the sky into 2 hemispheres, do you get the same correlation function?
So let's see. I don't know if I know the answer to that question offhand. I know that there is a northern variance anomaly, which is not quite the same thing. There's but close, but it's a 1-point function. Then there's a northern. There's other anomalies that are very close that definitely have a north-south part, and I'll get to the relationship between those and this in a minute. I don't know if exactly this thing is exactly this S1/2 has a north-south anomaly. It's probably been calculated. Many things have been calculated like this, so probably it's been calculated. Okay. So somewhere between 0.03% and 1% of realizations of the concordance model of inflationary lambda CDM have so little cut-sky large-angle correlations. And the other thing is that most of those do it in a completely different way. See, one way to get a low angular correlation function is to make all the C sub L 0, because then C of theta will be 0, and you'll have a low angular correlation function. But that's not what the sky does. So how does the sky end up with a low correlation function if the p-value of this is 10% and the p-value of the correlation function you get from all of these is 3 times 10 to the minus 4? What's going on? And the answer is that the sky manages to choose a C2 that cancels the contributions of these almost precisely. In fact, it's almost perfectly optimized to do that, to cancel them as well as it could. Okay? So to obtain S1/2 less than about 1,000 with the observed CLs requires varying the C2, 3, 4, and 5 and making them conspire against one another to cancel and give you a low S1/2. That's very strange in a model in which the ALMs are independent and which the CLs are independent variables. Okay? It means that they have to be correlated. It also means that even if we replaced all the CLs by their measured values up to L equals 20 and then did realizations of that sky, the cosmic variance would spoil the cancellation we see. You wouldn't get it back. Only 3% would have as low an S1/2, and most of those would not look like the data. They would have suppressed the C sub Ls. So if we want to explain the small S1/2 that WMAP said, it didn't go away. You can say, I never believe in a posteriori statistics, but actually it got about a factor of 200 worse in going from COBE to WMAP. You can say, I never believe anything less than, and depending what field you come from, you will choose some number here. I don't know if anyone chooses 20. And we'll talk about this in a minute. You might say, well, inflation can do that, but inflation, what it can do is change the C sub Ls. But I just told you that just changing the C sub Ls isn't enough. You have to correlate them. And so you seem to require some new physics that correlates C sub Ls, and so must violate the stricture that ALMs of different L are uncorrelated. Okay. So let's look beyond these just C sub L for departures from Gaussianity or statistical isotropy. And people have done this in many ways, and I'll only talk about a few of them. So let me talk about, if we see birds flying in the sky like this, we don't think they just randomly happen to do that. There must be some explanation for it. Okay? So what about, can we look at the sky and see, are there alignments like that? So the way I like to think about that is in terms of these things we call multiple vectors. You're used to one of them. You're used to the L equals 1 multiple vector. So if I asked you to tell me about the dipole of the CMB, you probably wouldn't tell me what A1Ms are. You would tell me some amplitude and some direction. Okay? And that's the L equals 1 multiple vector of the sky. So we can take the delta T, the Lth multiple of the sky temperature fluctuations, and replace the A1Ms by some direction and some amplitude. Okay? And this has nice properties because this really is a unit vector and A really is a scalar. And so it's a nice way to think about it. And the question is, can you do the same thing for higher multiples? And the answer is yes. You can take the Lth multiple and replace it by L unit vectors. And those really are vectors. They transform just like vectors when you rotate your coordinate system. The overall scalar really is a scalar. And so this is an interesting way to think about data on the sphere. We thought we had invented something really clever and new. Of course, all things new are really old. And so this, this representation in terms of actually much nicer in terms of directional derivatives on the sphere as a way of representing the multiples of a function on the sphere is something that this fellow, who you may have heard of, used in this little-known piece of work. So, and hasn't completely been lost. It turns out that geometrologists, for example, use this as a way to represent data on the sphere. Okay. So notice that the quadrupole has 2 vectors and the octupole has 3 vectors. So you can think of the quadrupole as kind of defining a plane and the octupole as defining the 3 planes. And we can look at the normals to those planes, the unnormalized normals. And we can ask where they are on the sky. So let me show you. I don't know whether to put them in the northern or southern hemisphere, so let me put them in the south. I'll put them in the north too, but let's focus on the south because it just turns out to be easier to look at. So here is the L equals 2 normal, that gray dot. And here are the 3 L equals 3 normals. Now remember, they're supposed to be independent of one another. They don't look independent of one another. They look like they're all in one little part of the sky. They also happen to be near the dipole. They also happen to be near the ecliptic. They also happen to be near the equinox. So maybe this was just some accident of the scan strategy or stuff. But once again, this turns out to be true no matter whether you look at Planck or you look at WMAP. It seems to be a feature on the sky of what is going on. Okay? That the quadrupole plane and the 3 octupole planes are aligned with one another with a p-value depending on which foreground subtracted map you have of typically closer to 0.1%. Okay? Now, Avi was asking about the difference between the north and the south, which is usually talked about as a power asymmetry or as a dipole modulation of the power. I'd like to argue that in many ways it probably should be talked about as the north being weird, okay? Low northern variance, and I'll show you why. Now, you can actually see it here. If you squint at this map of the sky, I think you can convince yourself that this part of the sky kind of has more going on than this part of the sky. Okay? And I know I've been very suggestive, but that's exactly what all these people found. Let's not go into the details of this plot. That's what this says. They looked at binned angular power spectrum on different parts of the sky. I'd rather look at it this way. So here is a PDF of the variance that you would expect on a hemisphere. Here's the PDF, there it is. And here's the south, the variance of the southern sky, and here it is sitting pretty much at the peak of the distribution at a p-value of 0.423, completely typical, maybe so typical that it's atypical, I don't know, but it is not weird at all. Okay? This is an, about L equals 60. Yes, yeah. And here it is on the north, way down here, at a p-value of about 0.1%. Okay, so the north has surprisingly little variance, and that's exactly kind of what you saw. And by the way, it's not actually optimized ecliptic north versus south. The galactic north versus south is just as good, and the optimum is somewhere that's neither. But it's like 10 degrees away from an ecliptic separation. Okay? Here's another one. It's the last one I'll tell you explicitly about now. So if we plot the C sub L's, okay, here they are. Here's the quadrupole, and notice that the octupole is a little higher than the quadrupole. And here's L equals 4, and then L equals 5 is higher, L equals 6, L equals 7 is higher, L equals 8, L equals 9 is higher, 10, 11 is higher, 12, 13 is higher, 14, 15 is higher, 16, 17 is higher, 18, 19 is higher, 20, 21 is lower. Yes? Yeah, sure.
So, I really like the idea of having more vectors on their space, but do you know what is the origin of them? I'm coming from the background of inflation, and one way to have them is that you just need to break the conformal invariance early on, and they get frozen as a scalar fit. So do you think there is any chance that any of those models would be favored? Because then you can have them on your backyard and we can just use them for that?
That's a great question. I want to save the answer till later, maybe till lunchtime, when I'll actually show a slide that why I think it's going to be very hard to explain it that way. Okay? Yes?
The dipole is 100 times bigger than all the other multiples.
Yes.
And so is it possible that there is some spillover of the dipole that is not subtracted properly that ends up producing this north-south anomaly?
The claim is no. Yeah. And people have looked at exactly that question. Is this bad dipole subtraction? It does not appear to be bad dipole subtraction. Yeah. So, you look at that, you have 9 pairs in a row where the 2L plus 1 is higher than the 2L. Okay? And that violates parity. Right? It says that the C sub L's of the odd ones are correlated with the C sub L's of the even ones. Okay? So there are many more. Okay? I've just told you about 4, and I've told you about 4 because of something that we did with those 4. So with so many anomalies, what are we meant to do? Okay? So because what typically people will say, well, each of these anomalies is 2.5 sigma, 3 sigma, maybe 4 sigma, barely. Clearly you're not going to overthrow all of cosmology with 3 sigma anomalies. You're not going to break this fundamental principle, which is really important because it allows us to do things, to invoke the ergodic theorem and for doing all sorts of things. This is really fundamental to how we think about cosmology. Clearly, you're not going to claim that the universe is not statistically isotropic. After all, maybe all of these things happen together. If you do one, you do all of them. If you happen to get a realization that has low S1 half, it'll also have north-south asymmetry. It'll also have quadrupole-octupole alignment. So maybe there's some simple that's not really that weird. It does seem to be there on the sky. We don't seem to have a good foreground explanation, and I can talk about each of them, why they're hard to explain with foregrounds. But maybe they're actually highly correlated with one another. And so let's take just a statistic for each of these 4 for representative. And we actually didn't choose these. These were chosen by another group what they did is they looked at the correlations between these statistics. Okay? And they said, oh, well, there's a mild correlation between S1 half, which was the lack of large angle power, and sigma 16, which is this north-south asymmetry. Okay? There's some correlation there. Not much correlation between any of the others, and they kind of left it there. And the thing is, they didn't quite ask the right question. Because what they're showing you here is the PDFs of the statistics. Okay? So they're looking at the peaks of the statistics and they're asking how are the peaks of the statistics correlated with one another. And that's not interesting at all because we're way out in the 3 and 4 sigma tails of the statistics. These aren't Gaussians. These aren't, these are complicated, highly nonlinear statistics. This is not instructive. Okay? I mean, it was worth doing, but it's what really you want to do is you want to ask, are the tails correlated? So here are the p-values of each of these statistics. And in the best case for lambda CDM, it would turn out that the PDF of all, the p-value of all 4 of them, the probability that the universe would have all 4 of these, is whichever one is the smallest. That, whenever you get, I don't know, whenever you get 2 times 10 to the minus 3, the worst low northern variance alliance, all the others, or 10 to the minus 3 here for S1 half, whenever you get that, all the others come along for free. And the worst case for lambda CDM would be if I was able to take all 4 of these p-values and just multiply them. Right? And the question is, where in between those 2 does lambda CDM actually lie? So that's what we looked at. So here we are with these 4 statistics. Okay? And it turns out that, in fact, the lack of full sky correlation, or cut sky correlation, so just outside the galaxy, is related to the lack, to the low northern variance. Okay? So if they had been completely independent, I would have taken, say, in this commander map, or let's take the SMICA map, because that's the one that I think people kind of, well, one of the two. Let's start with command. It's on top. 1.5 times 10 to the minus 3 is the p-value of S1/2 in this commander map. That's one of the ways of subtracting foregrounds. 3 times 10 to the minus 3 is the variance. You would multiply those together, and you get 4.6 times 10 to the minus 6. And it turns out that the joint probability, the joint p-value, is about 1 times 10 to the minus 4. In other words, about 30 times bigger. Okay? And that seems to hold true no matter which of the 4 cases. So those two are you're still getting an extra factor of about about 10, a little bit more in p-value. But that's all. You don't get to just multiply them. But all the others, you do. Okay. Pairwise, they have very little correlation. And if we then go say, okay, so let's take S1/2, those two, which are correlated, and then combine them with the other things, do we get any additional correlation between those? And the answer is, yeah, not really. That the correlation ranges from a factor of 0.6 to a factor of 2. So you can essentially take S1/2 and sigma 16, take their joint probability, here it is, 1.2 times 10 to the minus 14, and then you can nearly multiply it with the p-values of RTT, which is the parity anomaly or the quadrupole octupole alignment, to get what happens if you have 3. And if we put all 4 of them together, then what we find is that the total correlation factor, if you like, how much bigger this is than just multiplying all 4 of them together, is about 50. And so the combined p-value is, in the highest case, about 18 times 10 to the minus 8. And in the case of the NILC, 0. None of the 10 to the 8 realizations that we made had such a low, had all 4 of those anomalies. And the other two, the other two between 1 and 3 times 10 to the minus 8. Now, and this 7 map is the one that I'll say that people tend not to use for these kinds of things. It seems to have some other unusual properties. But anyway, all of these give you more than 5 sigma lack of statistical isotropy. So what does that mean? Well, it means that statistical isotropy is ruled out at more than 5 sigma unless you can find some explanation for this in the data. So what are some things that people say? And feel free now to good time to ask any questions you like. The first thing people will say to us is, well, you can't actually believe data without a model. Now, we thought that was really interesting. And we came up with some counterexamples. Like, for example, I think people believed in superconductivity after 1911 when Onnes discovered it, and before 1950 when Landau and Ginzburg came up with their theory and the much later and the later BCS theory. So that's an example. I think people believed in anomalous perihelion precession of Mercury in something like 1859 when Le Vernier measured it, certainly by 1908 after it was confirmed, and we didn't get GR till 1915, many decades later. And on and on. This is just not, this, I'll call it hyper-Bayesianism, is just not how, is not how science actually works when discovering new phenomena, right? So you can disbelieve a model, okay? You can falsify a model even if you don't have an alternative, okay? The other thing to really ask about is look elsewhere penalties, okay? And I'm happy, if you're interested, to tell you a little bit about why you should not worry about look elsewhere penalties here, because what I really wanted to tell you in about 30 minutes is that the universe is not statistically isotropic. Thanks.
Yeah.
Well, if it's not, I mean, our cosmic horizon right now is coincidence, right?
Is what?
So it's just happens to be that size,
right?
It's 13.8 billion years after the Big Bang, but
right.
The cosmic horizon changed over time, and so it's likely that if it's not statistically isotropic within the observable volume, it will be also beyond the observable volume, right? And so wouldn't that show something in the dipole? Like there should be some reason why we have the dipole, because there is some lack of statistical isotropy going to greater distances in some sense.
So, okay, so there, let's see. So if we were able to measure to larger volumes, if there are larger volumes, because of course at lunch I'll talk about the possibility that there aren't much larger volumes, that we are seeing pretty much everything.
I thought there was a paper claiming you can go 4,000 farther than the cosmic horizon, because otherwise, if there was a cliff, you would see it in the CMB.
Right. There may not be a cliff, but there may be periodic boundary conditions.
Ah, okay.
Right. It's right that there's no cliff. Right. In other words, there's probably not something imposing Dirichlet boundary conditions a little bit outside of the CMB, which is I think what they mean. But I'll talk about one potential explanation for this, as I'll talk about at lunch, is that there are periodic boundary conditions.
But then how do you get the dipole if it's periodic?
But the dipole, I mean, the dipole that we see is almost certainly our motion through the universe. Okay, so we have this large dipole due to our motion relative to the CMB. Okay? And the question is, how much is left, right, once you subtract that? And the problem is that you have to measure the dipole to better than 1% in order to start asking that question. And we don't have at the moment any way to do that. Okay? It's not clear if it's impossible ever to do. But it's certainly tough. So you can ask: is there a cosmological contribution to the dipole? And then you have to be very careful because of gauge ambiguities in that question. Okay, and how big can it be? Because actually, I and everyone who talks about the angular correlation function lies to you when they call it the angular correlation function. It's not the angular correlation function. It's the monopole and dipole subtracted angular correlation function. And so it's really weird that the monopole and dipole subtracted angular correlation function is 0. Right? So one of the things I'll talk about is it's kind of phenomenological things that one can imagine being consequences. So one can imagine that any real explanation for the absence, for the low angular correlation function is that it's actually the angular correlation function that's low, not the dipole subtracted angular correlation function. And that requires a very small dipole. It requires the dipole to be, I forget exactly what it is, like 20 or something like that. The cosmological one, so really hard to discover. So the fact that the octopole, the L equals 3, was a little bit lower than the theoretical prediction, and the quadrupole was significantly lower, and then the dipole will be even lower still relative to the theoretical contributions. If you want to keep C of theta, the real C of theta, the full C of theta, to be small. Yes?
Not my field, so this is a potentially ignorant question.
All questions are good.
How do we know that this isn't some weird foreground effect of some kind? Something in the galaxies, etc. I know that, yeah.
Yeah, so great question, and to some extent, let's see. So to some extent, let me go back here. The fact that all of these values are similar on this, and this, and this, and this, these are 4 different foreground removal techniques, okay, should give you some sense of what the systematic error is between them. Okay, so that's the first thing. Okay. And then you ask, and then solar system stuff. Well, let's see. So there's a few things, and it depends on the anomaly. First of all, the spherical harmonic structure. Now, there's the angular structure of, say, a galactic foreground, you would think would be well correlated to the galaxy. But for example, the quadrupole octopole pattern is actually a ring of extrema that are approximately perpendicular to the ecliptic. They look nothing like they are something that comes out of a galaxy structure. They're also something that's very hard to imagine getting out of a foreground. Okay? So how would you get a foreground that looks like that? Well, you might imagine that, for example, that there's some cloud of zodiacal dust that's out of the plane of the galaxy, that we're, out of the ecliptic, rather, that's, overhead, and people have looked for that. It would have to be, just a little bit warmer than the CMB, and they don't see it. So people have explicitly gone and looked for that. It would be a very strange thing in the galaxy. It doesn't coincide with any, for example, known, tail of some globular cluster, or some dwarf galaxy, tidal tail. So there does not seem to be a foreground explanation. The other thing is, foregrounds tend to add power, right? They don't subtract power. Right? So things like, if you say, oh, well, the quadrupole and octupole that you see are actually due to some foreground. Well, that says that the actual quadrupole and octupole are much lower than and then you change the S1/2 problem, but you make it worse. Okay? So again, how does a foreground remove power? Not remove photons, remove fluctuation power from the northern hemisphere, not the southern hemisphere. Yeah.
If the universe were rotating at some angular momentum, would that give you this anisotropy?
So great question. So some people looked at Bianchi 7H models. Okay, and what they did is they took the templates of Bianchi 7H's, which are a rotating solution, and they looked at, could we fit Bianchi 7H's to the pattern, and they found that that it is preferred to add a template of Bianchi 7H. It doesn't matter if it's rotating this way or this way. It should have what corresponds to an omega curvature of 1/2, which is inconsistent with what we would measure from higher L's. And if you do that and you fit it, they say, well, then you spoil the quadrupole-octupole alignment. They don't say it explains the quadrupole-octupole alignment or the hemispherical asymmetry. They say it gets rid of it. Okay, now, so you have to be really careful when people claim solutions to these things, because what they often mean is, okay, I do this thing, let's say I explain the cold spot. That's another anomaly. There's this cold spot. I produce a solution to that cold spot, and now I subtract that from the sky, and lo and behold, I no longer have low S1/2 and low and good quadrupole-octupole alignment, et cetera, et cetera. And but what you've really done is you've introduced a new mystery. Why did your solution, your new physics, your Bianchi 7H that you're adding, that doesn't explain the whole thing? You have to add it to the FRW piece, okay? So they don't say the universe is Bianchi 7H, but this Bianchi 7H template is adding it is a good fit, is preferred. It has a Bayesian evidence factor that's high enough that you would want to add it. And adding that, why that plus the other underlying cosmological fluctuations should precisely add up in such a way that you get quadrupole-octupole alignment and low S1/2 and low northern, et cetera, et cetera. And none of the explanations I know do that. They just spoil the anomalies, okay? So which isn't really an explanation. Do you?
Partly.
Oh, so
Because you have to suppress power. So
Right.
Yeah, you need cancellations.
Right.
You need chance cancellation. There's not that many modes.
you need chance. Well, the odds of getting those chance cancellations are about this. This is what the odds of those chance cancellations are.
Actually,
Huh?
I don't agree.
Why?
Why? This is what the sequence is in
You
minus
picked,
CDM.
you picked 4 things that you knew to be low, and you multiplied them together, and you didn't include the 40 things that people haven't complained about.
Excellent.
And that
Excellent.
would lead to more to reduced
Right,
Power.
right.
It's just-
So
it's
you're
very
saying this
hard
look
to do
elsewhere.
these things
I'm not
obviously.
paying look elsewhere penalties.
Yeah.
Okay, very good.
So, I mean,
Thank you.
But
Okay,
it's-
so
it's-
let's talk about.
it's not that everything has to go away, but it's not exactly as simple as saying that, oh, you just get to multiply.
Right, so let's see. Okay. So I call this the struggle between look elsewhere penalties and look more closely rewards. Okay. Because sure, I didn't tell you about some other, I chose these statistics, and maybe there are others out there that are, that aren't as anomalous or aren't anomalous at all, right? I divide the sky into 3 equal patches. Why didn't I do that? And 5 equal patches, and 75 equal patches, et cetera. So let's try to look at these, and I'll try to do that anomaly by anomaly. So S1/2, the lack of large angle correlations, which has a p-value of 10 to the minus 3. And so you could ask, why did I choose 60 degrees? Now, remember, this one is the one that's not really a posteriori because we saw it in Kobe. No one wrote down S1/2, but everyone saw that there was this weird thing. And it got about 200 times worse. In other words, the p-value with WMAP or Planck error bars is about 200 times smaller than with Kobe error bars for S1/2. So you could ask. It's just that Kobe has really.
10, right?
But the foreground subtraction is really bad. If you look at the values that they quote on their CLs, and you ask, well, what could I? We've tried this, and what we find is, that the range that you get. It's also the thing is, the p-value of S1/2 is a very steep function of S1/2, and so that's a lot of y. So it doesn't take pushing S1/2 up very much before you have a p-value that's much higher. Okay. So you could ask why 60 degrees for the lower limit, why 180 degrees for the higher limit. I would actually do better if I took it somewhat lower. 60 degrees, was optimized, I think, at 57. Why C of theta squared? Why integrate that? Why integrate d cos theta? So all of those, I can write down different statistics, and some of them might be better, some of them might be worse. There's probably other things that you could have done instead. I mean, this is a pretty natural thing to write down. If you say, is there as much large angle power as you expect, or correlation as you expected? So yeah, there's probably, there might be some look elsewhere penalty associated with S1/2. But I didn't show you the S1/2 of EE, which people have looked at. And it turns out it has the same weird property. It's sitting down there at 10 to the minus 3. And you might say, oh, but remember S1/2, E and T are correlated in lambda CDM. Surely those, the smallness of S1/2 of EE is because S1/2 of TT is small. And it turns out not to be true in lambda CDM, not if this is a fluke, which is the claim. So you have to come up with a look elsewhere penalty that's a factor of 1,000 if you want to argue with me about the fact that I only did S1/2 of TT. Okay. So in other words, that's what I mean by a look more closely reward. Okay. And it turns out, okay, so for the low northern variance, why north, why ecliptic, why did I smooth at 16? But if you actually go and look at, say, the Planck 2013 Isotropy and Statistic paper, you'll find ecliptic's not optimum. Galactic also gives you a similar p-value. There's also a low northern skewness with a p-value of about a couple of percent. There's a high kurtosis also at low end side of about 3%. So it's not just that you have low northern variance, right? It's that you have all of the low moments of the statistics are behaving strangely. And we just, people picked up the simplest one, the variance, to analyze, and got a small number. Okay. The odd parity preference, so people went out to Lmax. This was actually optimized, this Lmax of 27. And why odd versus even and not even versus odd? But actually, this is a really bad statistic, it turns out, of this anomaly. When I looked at the p-value of this anomaly, I said, how could you get such a ridiculously high p-value? Because the first 9 consecutive pairs have this relationship, And if I don't want to pay a look elsewhere penalty, I'd say that the probability of that is 1 over 2 to the 9, which is 1 over 512. And certainly I should pay a p-value of 2 because I could have gone the other way. So a p-value of more like 10 times smaller than this. Okay. Quadrupole octopole alignment. Well, I told you about quadrupole octopole alignment, but if you actually look at the original sets of papers about this, some of them, yeah. Yeah.
I think what you call the look elsewhere penalty is all the trials that you could have made, right?
Yes.
It's the same thing. So when you say, okay, it has to be 1,000, the penalty has to be 1,000 to explain it. How do I know what is the actual penalty? Is there a rigid,
No.
believable statistical?
No.
Bayes doesn't tell you, right?
There's no prescription for telling you what the look elsewhere penalty is. Someone said to us, well, you should write down all of the possible statistics that people could have written
That's the
down.
way I understand it.
But
Which can be a huge number, so.
right. So the question is, do you if you need to do that, I would claim that you could never falsify anything, any statistical prediction of any theory. That's the hyper-Bayesian view. That in order to do that, that the only way to do that then is to find another theory and show that it fits better. It doesn't happen to be how we've done science up till now. What we do is we tend, in this case, what happened is people wrote down a whole bunch of statistics that seemed like the right things to do if you were going to, test statistical isotropy. So for example, when we wrote down the statistics that found that for us found quadrupole octopole alignment, was actually found using a different set of statistics by De Oliveira, Tegmark et al. And Hamilton. And then the Land and Magasiu wrote a different set of statistics. When we wrote down those statistics, we were actually looking for a way to look for topology. We were not looking for this. And so, are there other statistics out there that people could have written down or did write down, and maybe they didn't report it because there's a reporting bias, right? But what I'm trying to say is, yes, I'm sure there are, but there aren't 100 different statistics that, 100 times as many different statistics that people wrote down and didn't report. There's maybe there's twice as many. Maybe they could have worked harder and come up with another factor of 4. That, there's a reason why what Feynman used to say, I never pay attention to 2 sigma anomalies, right? I do pay attention to 3 sigma. But we're out past 5 sigma here.
I don't think you're saying that fairly. I mean, if you take a bunch of Gaussian distributions and you make a random measurement from them, and each one of them will give you some p-value. But when you start to multiply them together to get an aggregate p-value, you are going to be increasing your unlikeliness as e to the minus 1 times the number of measurements you've made. So I don't think the issue is the factor of 1,000. I think it's something more like log of 1,000 in terms of the number of statistics you need to add to make a p-value seem very extreme. I'm not saying that. I mean, I agree that the alignments are weird, and I mean, so I'm actually not trying to say it all goes away. I'm just saying that I don't actually agree that taking 4 of the measurements that have been found to be irregular and multiplying them together, even with the correlations between them, actually makes it more convincing. I feel like and it's particularly because I don't think that now I'm changing topics, so I apologize, but it feels like the anomalies fall into sort of 2 categories. One is very large scale things, the octopole alignment, the correlation thing, the S1/2, the correlation function being small. That feels like a super large scale effect, whereas the power asymmetry between hemispheres is at a noticeably smaller scale, and so that
in fact keeps extending out. So
I'm not quite clear that we're even talking about one type of anomaly, because it's not obvious to me how the thing that would cause things to look different at the 10 gigaparsec scale to get the S half and other very, very low L effects to happen. it's going to be particularly obvious how to couple that to power L of 40 in different hemispheres. It's just not clear that's actually going to be the same type of explanation. So
It's-
those seem hard to combine.
But if you like, I'll give you the S1, give you the low northern variance because it only got me a factor of 10. You're saying that's the one that's most correlated to S1 half.
Yeah. Well,
So
no,
what you're saying is actually most of the signal probably is coming from the lowest L's for that one, right? It's that was the one that was going, the product of those two, the combined p-value of those two was 10 times smaller than the smallest of the smaller of the two p-values, as opposed to 1,000 times smaller. So in fact, those ones are closely related.
Okay.
And interestingly, the hemispherical asymmetry, there's actually evidence that extends way up into the many hundreds, because if you regard it as dipole modulation, which is another way of looking at it, then although the amplitude of the dipole stops being significant after like about L of 60, the directions of the dipoles that you would fit for dipole modulation keep being in the same direction up to L. I've seen claims of 1,300. I mean, I haven't done this myself, but the published claims are that it's way beyond the low L's, that the directions stay the same.
So
Suggesting
what's the prediction for large-scale structure in that?
that's a good question, and I think probably the answer is you have to take, you need a better model, because it's not a model, it's just a phenomenological fit, right?
But we do have data sets of radio sources on the sky, X-ray sources. Wouldn't you expect some anomaly to appear between the two? I mean, nobody looked into that.
There's so many things I don't know if anyone's looked into that.
Okay.
We haven't looked into that one.
Are there any explanations which, for example, can simultaneously explain 2 or 3?
So
That will make it.
So what I'll talk about at lunch is, okay, so let's see. If you look at which L's are connected, okay, which harmonic coefficients are correlated. So people wrote down something called the BIPOSH expansion, bipolar spherical harmonics, which is just saying, it's just think about these as angular momentum additions. If I have two L's they're separated by some capital L, what's the strength of the capital L modulation? Okay? And the capital L equals 1 is almost 4 sigma anomalous, and that extends, it turns out, it's large at small l, goes to 0 at around 30, but then there's another bump at around 150 or something like that. So that's, that is the strongest evidence for. But then it turns out that although no other individual BIPOSH power is anomalous at 3 or 4 sigma, that all of them are sitting, as anti-correlations out to about 27. So the distribution is all on one side of the Gaussian. Some of them are near 0, but some of them go down to -2 sigma, right? Out to about 30. Okay? Which says that the L structure of whatever is causing this is not simple. And that's why, for example, adding a single vector field to an inflationary model seems to me to be unlikely as an explanation. Now, it could be that it'll almost certainly be that some of the things we see are accidents, like the fact that the ecliptic plane has anything to do, or the galactic plane has anything to do with cosmology seems very unlikely, right? But some of them won't. And I guess what I'm suggesting is that the likely explanation will be something that has a more complicated L structure than a single vector. And I'll talk about topology as a potential explanation. So, has anyone written down an explanation for multiple anomalies? As far as I know, the answer is no. But topology has the landscape to be such an explanation. Actually, there is a topology which has been shown to be the explanation for both S1/2 and quadrupole octupole alignment, but not the other two.
Thank you. Yeah.
Any other quick questions? So if not, let's thank Professor Starkman for a very interesting talk and the discussion. I think Glenn will have another talk on the launching.
He will explain what he
Yeah.
taught us.
Yeah.